Hi everyone. Today we're going to continue with the combination of proofs and set theory. So this proof type is called element chasing proofs. So we're really trying to prove things about subsets and sets belonging to intersection or union of other sets. So here, this theorem that we're going to start with is if both A is a subset of B and A is a subset of C, then A is a subset of B intersects C. So the first thing I'm going to do is just kind of prove this to myself with a small subset here, so or a small just set. So let's let A equal the sets 1, 2, 3. B is the sets 1, 2, 3, 4, 5. And C is the sets 1, 2, 3, 4, 5, 6. So as we can clearly see, A is definitely going to be a subset of B because they have 1, 2, and 3 in common. So we can just highlight these here. So A has 1, 2, and 3, and so does B. And then A is a subset of C because C also has 1, 2, and 3. So again, subsets just mean that all of the elements in A are in B and C as well. So now that we've kind of shown this first part here, that A is a subset of B and A is a subset of C, let's see if A is a subset of B intersects C. So let's just go ahead and do B intersects C. So this is going to be 1, 2, 3, 4, 5. Intersect with 1, 2, 3, 4, 5, 6. So the intersection between these are going to just be actually all of B. That won't always be the case, but here it is. And we can see that the set containing 1, 2, 3 is a subset of the set containing 1, 2, 3, 4, and 5. Therefore, A is a subset of B intersects C. So we've done this with just a small proof, just proving it to ourselves, because if for some reason this statement wasn't true, this theorem, then we wouldn't actually want to prove this. Then we would have just have found our disproof. So a lot of times this is easy to start with what you know and what you want to show. So we haven't done this necessarily in direct thought, but I've mentioned this before, where you have an if statement and you know the if part is true because you've assumed it to be true, and you're trying to show the then part. So sometimes it's good to just start with what you know, what you want to show, and just kind of work your way through the middle, either backwards from what you want to know or show and from what you know. So let's just create kind of a walking flow of where we're going. So we know the if part. We know that both A is a subset of B and A is a subset of C. So we need to think of, usually when we know something, the if part, we hit it with a definition. So let's hit it with a definition of a subset. So by our definition of subset, we get the next block that if X is in A, then X is in B. And if X is in A, then X is in C. We want to show, so that we've kind of hit a roadblock here. Well, I know X is in A, X is in B, then X is in C. Okay, maybe I'm not really seeing where this is going, so let's go ahead and do the end part, what I want to show. I want to show that A is a subset of B intersects C. So in order to make this conclusion, I had to have defined this subset here. So I had to have gone from this block here to get to here. I had to have gone that X is in, if X is in A, then X is in B intersects C. So I had to have just shown this idea here in order to get to this part over here. So I need to figure out a way to connect these two blocks here, because this is what I know based on my if statement, and this is what I want to show based on my then statement. So I need to figure out a way to connect these two yellow blocks here. And we're going to do that with what is known as element chasing. So let's actually just get started with our formal proof. So proof, assume, assume both A is a subset of B and A is a subset of C. So again, by definition of subset, we know that both, if X is in A, then X is in B, and if X is in A, then X is in C. So I can't necessarily say for sure that I know X is in A and B. I have these if statements here that's saying if X is in A, then X is in B, and if X is in A, then X is in C. But we can't necessarily say for sure that there does belong something there. X could be nothing. These could be the null sets. But it's also true that a null set is technically a subset of a null set. So we need to take this with a grain of salt as moving forward. But in order to prove this, again, I want to show the following. I want to show that this is a subset here. So I'm going to make a claim, and I'm going to try and prove this claim. So let's say consider the following claim. If X is in A, then X is in B intersects C. So this is what I want to show, because if I can show that this statement here is true, then I have shown what I want to, then I can go to the next step and apply the definition of subset and say that A is a subset of B intersects C. So this is what I want to show. So if I can prove this claim here, I can prove the overall theorem. So let's go ahead and just try and prove this claim. So this is an if statement that we have here, so we're going to assume the if part. So assume X is in A. So here, I'm allowed to assume that X is in A because I've just made the claim saying if X is in A, then X is in B intersects C. So I'm allowed to assume X is in A because that's the if part here. What I can't assume is that X is in B and C. So I need to show us somehow that X is in B intersects C. So I'm going to assume the if part here. So by, well, not yet. We don't want to hit with the definition yet. So assume X is in A, since A is a subset of B, by definition of subset, X is in B. So this is a really nuanced thing because you may be thinking, well, didn't I already know that X was in B because I set it up here? But be careful because, again, it goes back to the point that if X is in A, then X is in B. I don't know that X is in B. It's contingent on X being in A. So since I've just said X is in A, that is confirmed. Now we can apply this this if statement. So because I have shown that X is in A, then I can go ahead and use the fact that since X is in A, X is in B, because A is a subset of B. So then I can also say, well, since A is a subset of C, well, here we've just said, again, if X is in A, then X is in C. So because I, again, have said, yes, it is true, 100%, X is in A, I can now unlock this if statement and say, all right, the if part is true here, X is in A, then we can go ahead and say X is in C. So since A is a subset of C, by definition of subset, X is in C. So now I've just concluded that X is in B and X is definitely in C. So now the key to all of this, the key to linking these two statements here is the definition of intersection. So just to remind us our definition of intersection, we have, this isn't vital to the proof, well, it is vital to the proof, but it's assumed that you already know what the definition of intersection is. So we can say intersection is X is in B intersects C if and only if X is in B and X is in C. So this is an if and only if statement, so it works both ways. I know this part here, so now I can go ahead and conclude the beginning part. So by definition of intersection, X is in B intersects C. So I've just proved my claim. And so now I can say I've proven if X is in A, then X is in B intersects C. Therefore, and again, this is the connecting piece because I've just shown this box here, and now I can make my concluding thought. So therefore, by definition of subset, A is a subset of B intersects C. And that's the end. So in all of this, we can't get lost in the elements necessarily because we're trying to prove overall a subset. We're not trying to prove that there's an element in the set and that element is also in this other set. That is the supporting definition that will give us the definition of subset. So that's why this is called element chasing. So we're trying to get all of these elements together, and then once we've got them where we want them, then we can make the final statement that we have a subset because the elements belonging to sets is the definition of subset. So I know that these can be kind of confusing, so let's just do another example so that we're all on the same page with how these work. So let's look at another theorem here. If both A is a subset of C and B is a subset of C, then A union B is a subset of C. So again, let's just try and quickly prove this to ourselves, because if we can't prove it to ourselves, then we have just found a counterexample. So let's let A be the set containing 1 and 2. Let's let B be the set containing 2, 3, 4. And let's let C be the set containing, I don't know. 6. Let's just keep C the same, 1 through 6. So let's say, okay, so we know that A is a subset of B because, or C, excuse me, because we have 1 and 2, 1 and 2. And we know that B is a subset of C because we have 2, 3, 4, 2, 3, 4. So let's do the union of A and B. So A union B is 1, 2, union with 2, 3, 4. So again, union is just combining everything together. So 2 is already in both of these, so we're not necessarily just going to have the common mistake that I see a lot of times is people just saying, oh, well, it's just adding everything here and everything here, so I'm just going to have 1, 2, then 2, 3, 4. Well, these are the same elements, so I don't want to write those twice. So anything that's the same, that's common between the two sets, just you only have to write it once. So now the union of A and B is 1, 2, 3, 4, and let's go ahead and look at our C, and see, is this a subset? So we have 1, 2, 3, 4. Yes, that is a subset. All right, so we've proven this to ourselves, and so we want to just again start with what we know. We want to start with our if here. So let's go ahead with proof. Assume both A is a subset of C and B is a subset of C. So once we assume something, we want to hit it with the definition. So by definition of subset, if X is in A, then X is in C. If X is in B, then X is in C. So let's again make a claim. So just as before, in our theorem, we're trying to show this. In order to get to this point, we need to have just shown the definition of subset. So we need to make this into an if-then statement. So if X is an element of A union B, then X is an element of C. So that's what our claim is going to be. So claim, if X is an element of A union B, then X is an element of C. So our proof of the claim, we can assume the if part. So assume X is in the union of A and B. Then we want to hit it with the definition. So by definition of union, either X is in A or X is in B. So this is the tricky part here, because in the previous proof that we did, we only needed to know that X was in A, and we were good. We knew that, and so we could unlock these if statements up top. However, I can't say for sure that X is in A, and I can't say for sure that X is in B. I know that it's in one of them because it's in the union, but just as we've done in this little proof over here, 4, let's take 4 for instance, 4 is in B, and it's in the union, but it's not in A. So I can't say for sure that X is in both A and B. I know it's in one of them, and I know it's in the union. But just as we showed here, I know that 4 is in B, and it's in the union, but it's not in A. Similarly with 1. I know 1 is in A, and 1's in the union, but it's not in B. So we can't assume that X is in both A and B because that's not our definition of union. It's in either A or B. It could be in both. Let's take, for instance, 2. 2 is in A and 2 is in B, and obviously it's in the union, but again, that's not our definition. It's in one or the other. Could be both, but I don't know for sure. I don't know what X is, and I don't know what this A and B sets are. So that means, and hopefully the either or statement triggered this for you, we need to do a proof by cases because I know it's in A or B, but I don't know both. So now we need to do a case situation. So this is kind of a nesting proof, as you can see, but such is life. So sometimes that happens. So consider the following cases. So case 1, assume X is in A. So here, since A is a subset of C, we already know that. That was in our if statement of the original claim. So since A is a subset of C, by definition of subset, X is in C. And that's what we wanted to show. We wanted to show that X was in C. That's what we had up here. That was our then statement. So pretty short case, but that's the case. So case 1, X is in A. Since A is a subset of C, X is in C. We're done. That's it for the case 1. So case 2 is going to be the same amount of, or the same length here, pretty short. So assume X is in B. Since B is a subset of C, by definition of subset, X is in C. And again, that's what we wanted to show. So we've shown that X is in C in both cases. So closing out our claim up top here, having shown X is in C in all relevant cases, we conclude if X is in the union of A and B, then X is in C. So now I've just proven my claim here, but again, I need to close out the overall proof. So we've shown X is in if X is in A union B, then X is in C. Therefore, or I think I used this notation once with you guys before, the 3 dots. I think from now on I'm going to use the 3 dots. Therefore, by definition of subset, A union B is a subset of C. And that's what we wanted to show. So you can see that there's a sort of pattern going on here. The key part to this proof was the proof by cases, and you should have, if not here, maybe in the future, think, if I have an either or statement, I need to use cases. So just like our previous proof methods, sometimes you're going to use multiple methods in one proof. So you're not done remembering all those other proof methods. They're going to come into play here. So I really suggest doing these two things that we did in the beginning. Just one, showing it to yourself first. Is it actually true? Because if it's not true, then don't waste your time trying to prove it, because you're going to have a hard time, or there's going to be small slip-ups that aren't necessarily true. And then start with what you know. So assume the if part, hit it with the definition, apply what you want to show, the then part, and then try to work your way backwards, and then fit the connecting pieces together. If this flowchart works for you, great, use it. If it's too clunky and it doesn't make sense to you and you just want to dive right into the proof, that's fine too. So whatever method works best for you, use it. You will have, you don't have a formal classwork today, but tomorrow you will have a classwork due, and I will be available on Zoom if you have any questions tomorrow. So today, your only thing to do is just fill out the Google form, and then tomorrow we'll have a Zoom call, not today. Tomorrow we'll meet, and then you can ask any questions that you may have on element chasing. All right, so have a great rest of your day, everyone.